Good evening, everybody. Till now, we have learnt about DC circuits and also about single-phase AC circuits. Today, I'll introduce you to three-phase AC circuits. Okay. Why do we need to learn three-phase circuits? So, if you see, most of the machines where there is high torque requirement, like a railway engine or an automotive vehicle, electric automobiles, there is it uses three-phase motors. Okay, so they generate a lot of torque as compared to a DC motor or as compared to and single phase AC motors. So that is why this is very widely used in three phase motors. So that is the reason we are going to study about our three phase systems also. The three phase motors, like again it's shown here, three phase motors, heavy duty motors, transmission, basically transmission of energy from place A to place B, all the transmission lines which we see in our day-to-day life in the commercial power supply grid, they are all three-phase systems. So we'll see as we learn more, we'll understand what are the advantages of three-phase supply. Similarly, welding machines which generate a spark by producing an very high voltage, so they also draw a huge amount of power, so they also generally use three-phase systems. Okay. Having talked about that, so what is the basic difference between a three-phase and a single phase? So in a single phase system, like you generally have a permanent magnet, and then you have an it could be a permanent magnet, or it could be again a field winding, either way. So you will have a coil which is rotating, so that will generate a single phase. Okay, so if you see in one rotation, mechanical rotation, the energy, okay, is drawn from the circuit in a sinusoidal manner, where you have a peak voltage and you have a negative peak voltage. Okay, whereas in a three-phase system, basically you have three pairs of poles. Here, instead of moving the coil is put on the stationary, and the field winding is put in the rotary. So it just swapped. So this has got a more advantage. Okay, that we learn when we learn about the generator aspects. But just to give you a brief idea, you have a rotating field and you have three sets of coils, the armature coils, which are stationary, and if you see, they are spaced physically at 120 degree apart. Okay, so this is the red one. If you see, there, that is the one. Then you have the green and a blue. So as this coil rotates out here, so they will induce voltages, since they are spatially spaced, like total degree of is 360 degree in one rotation. So you have three sets of coils, so 120 degree will be the phase shift. So these three voltages will be induced in these three coils, which will be out of phase by 120 degrees. So this is known as a three-phase system. Okay, wherein instead of a single coil pickup, we have three sets of coils. So obviously it has got a great advantage over, because if you see in a single rotation, you are tapping energy at three coils. Obviously it will require more torque will be required to rotate it, but then still the conversion efficiency from mechanical to electrical, which will be much better. Same holds good when we are driving a motor. So the efficiency, when we supply if you have a single phase supply and a three phase single phase motor and a three phase motor, so the conversion efficiency from electrical to mechanical power will be much better in a three phase motors. Okay, in a single rotation, since there also you are giving three set of coils and they are trying to rotate a single set of rotor. All right, so that's why the efficiency will be much better in a three phase motor. So what is it known as? Now you have something known as a balanced three-phase voltages. Okay, what is balanced? That is, you have three sets of coils which are placed 120 degree apart spatially, and they generate 120-degree out of phase signals. We say balanced because the total number of coil windings is same in the 3 set of coils, and they generate the magnitude of the voltages which are induced is exactly the same. Only difference, so the frequency and the magnitude remains same. Only difference between these 3 signals will be in phase, which will be 120-degree apart. Okay, so that is why we called it an balanced 3-phase voltages. Okay, balanced means the magnitude remains same, and for that to remain same, essentially we should have the same type of coils, same number of same diameter of the coils, and same number of turns, and they should be exactly physically exactly the same, these coils, okay, in geometry. So they will induce the same voltage in all the 3 coils. These are the 3 voltages in the 3 different coils. So if you see, this is the first voltage which is shown in blue, then you have and a second which is shown in red, and then and then in green. So if you see, we can say the green one, okay, the green phase is lagging the first red one by 120 degrees. So see, this is crossing 0 here, this is going to cross 0 here after 120 degrees, right? So that is why we call the phase 2 lags phase 1 by 120 degree, and then phase 3 is this blue one. So you can call phase 3 is lagging phase 2 by 120 degree, or alternatively you can call phase 2 leads phase 3 by 120 degree. And also the phase difference between phase 1 and we can call phase 3 is lagging phase 1 by 240 degree. Okay, or it is all the same, you can call it is leading by 120 degree, because the overall is 360 degrees. So either way you can look at it. Okay, so these are the kind of waveforms which you get to see when you put these waveforms onto an oscilloscope. Okay, if you're going to put these 3 signals on the 3 channels of an oscilloscope, then these are the kind of waveforms you can see. So now they could be the way the coils are arranged in the source. There are 2 types of 2 configurations. Okay, one is known as an Y connected source, and other is known as a delta connected source. In the Y connected source, on the left hand side you can see this is known as the Y, in which you form an star network, and then you also tap an line from the junction, which is known as the neutral. So you have 3 live wires in which voltages on a 120 degree out of phase voltages are induced, and then you have a neutral also out here. Okay, similarly you can have a delta connection. Okay, so if these coils are connected forming a triangle, then they are known as the delta connection. In this case, only 3 lines are required to transfer the power from place A to place B. Here there are the requirement is of 4 lines. Okay, but this is the one which we generally use for transmission of power, that we will see the reason very soon. Okay, so this is if this is clear, this is a star network or a Y connected, and this is a delta connected source. Okay, these are the 2 configurations which are available. Now if you see, this is all ideal voltage sources, but for any practical network generator, you will have all these coils, armature coils will have some amount of inductance and also resistance also. So this is how a practical generator would look like. Okay, there will be some RW stands for R winding. Okay, so there will be some internal resistance in the winding, right? So that is known as an R winding, and also there will be some inductance which is associated with these coils. So this is how a practical generator would look like, equivalent circuit, and this is the equivalent circuit of a practical delta connected source. Okay, here also you will have R winding and also an inductance of the winding. Okay, so these are the 2 kind of so practical sources what we have. Now you have a balanced in a balanced Y connected system. Okay, these three voltages we said they are equal in magnitude, and they are only differ by each other by a phase. So if you take the algebraic sum of all these three, if you add these two, you will get somewhere here. Okay, and then if you take the algebraic sum of all the three, it will come to 0. Okay, so that is what is known as a balanced phase. So if you add VAN, VBN and VCN, you will get 0. So if you do the vector addition, if you see the vector addition of these two will generate an vector like this, and they two will get cancelled to each other. Okay, so so the vector sum of all these three voltages are 0 for a balanced phase network, and also the magnitude of these three will be the same. Okay, so this is what an balanced phase means. Okay, so we got to remember these things. Again, here now in this, these voltages are known as the phase voltages. Okay, this is the one phase voltage, second phase voltage, and third phase voltage. Okay, so the phase voltage is like for AN, it is known as we are going to represent it by VP, and then we are going to assume that this is 0, so that the next phase will be minus 120, and the third phase, again if you see the magnitudes are same here, and the third phase will be minus 240, right? Or you can write it as plus 120, it doesn't matter, so it means the same. So you have three phases, all the magnitudes are VP, which is VP stands for phase voltage. Okay, now please don't confuse it with the VP as V peak. Okay, it is not a peak voltage, it is just a P. P stands for phase. Okay, and VP generally means RMS value of the phase voltages. Okay, so here we are not going to mostly we are not going to talk in terms of Vm sin omega t. So that Vm, the max voltage, we are not going to discuss too much. We are going to talk about RMS voltages only. So this RMS voltage is VP stands for RMS voltage. You got to remember that. Okay, so this is RMS voltage VP. Okay. Now in a Y connected, we call, I told you what is phase voltage. Phase voltage is the voltage between each of these phases and the neutral. So in the commercial supply, what we get at our home, it is generally 230 volts. So between one phase and the neutral you have 30. From the second phase again to the neutral you will have 30. From the third phase also you will have 230. Mind you, 230 is the RMS voltage. Okay, the peak voltage will be obviously into √2 times. So we are talking about RMS voltages. Okay, so also at the substation or at the wherever the electricity is being generated, the neutral is grounded out here. Okay, and for an ideal transmission line, there will not be any current flowing which will be flowing into this neutral wire, all if the loads connected are balanced. Okay, so there will be no IR drop in the neutral line. Okay, there will be no current has to flow, but practically the loads don't get balanced exactly, so there will be some amount of current. Okay, but still it has to be within permissible limit. At our home also, we will have a ground, and we have this neutral wire which is coming from the substation, and then we need to measure this voltage between the neutral and the ground, and generally it has to be less than 3 volt. If it is more than 3 volts, that means the loads are not balanced properly. If the loads are balanced properly, greater voltage from neutral to ground just means that there is a lot of current which is flowing into the neutral wire, and the currents are not balanced. Okay, so you have to be whenever we have a connection at home, we got to ensure that the neutral to ground voltage is less than 3 volt, and which indicates that the loads are balanced properly. Okay, so this is the phase volt. These are known as the phase voltages, VP0, minus 120 and minus 240. So the phase changes, whereas the phase magnitude of the phase remains same. The angle with respect to each other, they are 120 degree apart. Okay, similarly, this is the phase voltage. It is measured between the neutral and the line. Okay, so line to neutral voltage is known as the phase voltage. So these are the three lines. Okay, red, green, and here it's red, orange, and blue. So you can have any color code. So those three line voltage lines, the voltage between those lines and the neutral line is known as the phase voltage. Okay. Now you have something known as the line voltage. Okay, a line voltage is the voltage measured between any two of the three lines. Okay, so you are not considering the voltage between the line and the neutral. We are between these two lines. So if you see that voltage is, if it is 230, if between phase to neutral is 230, then phase to phase it will be 440. So why should it be 440? We will do the derivation here, but we can visualize it here also. If you see this phase 1, it is going in a maximum. So this is the neutral. So phase to neutral. So this is the V peak. Okay. Whereas between if you are going to have a load connected between phase 1 and say blue line, so when this is going maximum, so instead of an 0 like in the earlier case where you connected neutral, now we are going to connect the other line. So if you connect the other line, if you see here, this voltage is much higher than this peak, right? Because this is a negative when this is. Similarly, when the green is going on the peak, you will find the other two are in the negative. Similarly, when the blue is in peak, so if you try to take drive a load between two phases, so the voltage will be much higher. Okay, so in our domestic use, all the loads are designed only for single phase and neutral. So if you are going to connect a load between two phases, then all your normal tube lights and whatever you have, domestic appliances which work in single phase, they are going to burn, because you are going to apply a much higher voltage. Okay, now what is that voltage? How much voltage would be there between two phase? So in this case, I told for 230 phase voltage, the line voltage would be 440. So we can derive that also. So it is the phase voltage will be √3 times the line voltage will be √3 times the phase voltage. Okay, where does this √3 come from? Okay, so this is like, right, the between VAN, that is known as the phase voltage, is VP0, VBN will be VP minus 120, and the third phase voltage will be plus 120. Now if I am going to talk about a line voltage, so I need to take the difference of these two, right? This I put a plus out here because this is neutral to B. So AN minus BN. So okay, because I am talking about now the voltage between two lines instead of line and neutral. So I do AN minus BN. So VP0 minus VP 120, right? So if I write it in polar form, okay, this 0 is just 1 and this 120 is cos 60. If you say 180 minus 20, so half plus √3 by 2. So we write in this form. So you get the, again you convert it back into polar form, you get an √3 VP. So if you see the magnitude, the line voltage magnitude is √3 times phase voltage. So this is very, very important, that the line voltage is going to be √3 times the phase voltage. Okay, so and what about the angle? Now see, this was the first phase, this was the second phase. So when you take then when you take a vectors difference of these two, okay, Rn and Ry. So when you take a vector difference, so this blue line is negative of this, and then this is the vector sum. So you will find this will be 60, so this will be 30. Okay, because these are all of equal magnitude, right? So you will get 30 degree. So and 30 degree it is going to lead from Rn. Okay, so I am taking an signal between Rn and Ry. So the net result will be a signal which is leading by 30, and the magnitude will be √3 times the phase voltage. So this is a very important equation. So you get an √3 times Vp and phase leading by 30. Okay, now what about the other two? So similarly you can do the subtraction for the other two also. So you in all the three cases you will get an root 3 Vp as the line voltages will be root 3 times and a Vp. Okay, Vp is the phase voltage, and now between these three line voltages they will be 120 degree apart. Okay, so this is 30 minus 180 will be so minus 90, and again minus 90 minus 180 minus 210. Okay, so the line voltages are root 3 times phase voltage. So this is a very important thing which we need to remember. So now you have this a Y connected or a star connected source which is driving an three-phase system load. Again this load is also connected as a star. We'll see different configurations. So the first condition is where an Y connected and a source is connected to an Y connected load. So this is, so if you have, so this is known as the wye-wye connected system. Okay, this is Y source and Y load, so it is known as wye-wye connected three-phase system. So if you try to, this is find the currents which are flowing in this system. So this is known as the this current is known as the line current. Okay, line current is the line which is going to connect the source and the load. Okay, now the phase current. Okay, remember now we are introducing new terms. Okay, the phase current is the current which will flow into each of these loads. Okay. Like the current which is going to flow in ZX, ZY, and these are all same. That is why they have been shown as ZY, ZY, ZY. Otherwise, okay, there are three arms. Balanced means again they all have to be equal. So that is known as the phase current. Okay. So the current which is which would flow here. Okay, what is the voltage across Zn? It will be the phase voltage, right? Because it is the voltage between single phase and the neutral wire. So that is why the Ia will be phase voltage divided by the impedance. Okay. Similarly, Ib will be this phase voltage. Okay, divided by again the same impedance. So again since that voltage is lagging the An by 120 degrees, so you will get the current which is flowing here is also lagging the first current by 120 Ib. Similarly, Ic will be lagging Ia by 1. Again, if you see all the three currents, they'll have the same amplitude. Okay. Because again the voltage is same, the impedance is same, so the magnitude will be same. Since the three voltages are differing each other by 120 degrees, the currents also will differ each other by 120 degrees. Okay, so that is how. So in this case also since this is a balanced load, the vector sum of these three voltages will be 0. Same happens with the current. The vector sum of all these three currents will be 0, and there will be no current which will be flowing in the neutral wire. Okay, so the current in the neutral wire will be 0. Okay, so these are the three currents which will flow into. Now what is very important here is for an wye-wye connected system, okay, the phase voltage, okay, and the line voltage are given by an equation. Line voltage is root 3 times an An. Okay, whereas the phase current and the line current are same. Okay, so that means phase current and the line current for a wye-wye connection is same, because this is the currents which are going into the in the line. Okay, from the source to the wire. And what is the current which is flowing into each of these elements? It is the same current which is flowing, because that will not be the case in a delta connected. We will see subsequently. So in a Y connected load, the phase current and the line current are the same. Okay, so these two things we need to remember for a Y connected three phase systems. Okay, so if you take an example, it will be even more clear. So this is one voltage. Okay, these are the balanced source. You have 110 volt. this is also 110, this is also 110, but the phase is 0, minus 120 and minus 240. And whereas this is the source impedance, which is now 5 minus J2, 5 minus J2, 5 minus J2. Okay, and then you have an Y connected load which is an 10 plus J8. Okay, so this is an capacitive load. So just for numerical appreciation, it's put as minus, otherwise it could be plus also. Generally, if it's an inductor, it has to be plus, right? Okay. So these are the three loads which are connected. So if I have to compute what are the currents, so first I need to find out what is the total impedance. So it will be 5 minus J2 and the sum of this. Okay, 10 plus J2, so 10 plus 8J. So I get as 15 plus J6. So which is in a polar representation 16.155, and angle is given as 21 degree. Okay, so so this is the total impedance. And what is the total current? Total current is the phase voltage divided by the resistance, total impedance. Okay, in this case, so which you will get 6.81. Okay, so now if you see, this is you don't have to compute the currents in B and C. So whatever we get, minus 21.8 and minus 120, which will give minus 141. Again, you can either from here you can add 120 and you can get the current phase for the third component. Okay, so you don't have to do this division for all the three, because all the three magnitudes will be same, only the phase would change. Okay, so this is how we compute the three phase currents. Now in this case, the phase currents and the line currents are going to be the same. Okay, so now what will here in this, if you see, the phase voltage is 110, the line voltage will be root 3 times 110, and the line current and the phase current are going to be the same, and the value will be given as 6.81. Okay, so now you can also have an delta connection out here. Okay, here you have an connection which is a star from the source side, whereas on the load you have an delta connection. Okay, so what happens here? So if you see here, just by seeing itself, we can say that the voltages across each of these impedance will not be the phase voltage, but it will be the line voltage, because this impedance has been connected across two phases and not across the line voltage and the neutral, right? So if you see this arm, okay, it is what are the voltages applied? B and A, right? So that means across these across this we have a line voltage, that is root 3 times of the phase voltage is applied across all these three. And also the second thing what we can see here is this line voltage is not same as phase voltage, right? So if you see here, this is the line current, sorry, the line current is coming here. Okay, that is getting divided into two phase currents out here. A phase current is the current which goes into the each phase of the load, right, from the load side. So if you see in the load, this is the line current which is coming, whereas in the phase it is getting diverted into two branches. So here also here the line current is not same as the phase current in this. In the earlier schematic, this didn't happen. So this is the same current which was coming was flowing here like this. Okay, so the line current and the phase current was same here, whereas here the line current and the phase currents are it's not going to be the same. Okay, so we'll compute that, how to go about doing. So the voltages across each of these loads are going to be root 3 times the phase voltage, because we are that, like we discussed, we are going to apply line voltages across these impedances and not phase voltages. So that is why VAB, VBC, they are going to be the root 3 times phase voltages which we are going to apply across. And to compute the currents, now VAB divided by the impedance. Okay, so this is going to be root 3 times the phase voltage. So that is why the currents will be root 3 times and greater here, out here, right? Okay. Now what about the line current? Now the line current is going to be the algebraic sum of these two signals. Okay. So like we did in the last case, okay, we did an algebraic sum of the voltages and we got an root 3 times the resultant was root 3 times the single phase voltage, right, in the previous case. In this case, same thing, we are going to add the phase currents out here to get the line current. Okay, so if you do an algebraic vector addition of these two currents, okay, you will get root 3 times the phase current. The line current will become root 3 times the phase current. So if you see, the line current here is root 3 times phase current in a delta connection. Okay, so this is a delta connection. If you see, the current will be the same derivation which we did last time. Now the line current is root 3 times I phase. Okay, so here you will find across these in each of these here you have the voltage across this is root 3 times phase, and the current which is flowing out here in the line is root 3 times the current which is flowing here. So these are the two major differences between an wye-wye connection and wye-delta connection. Okay, so if you take an example here, it says a balanced ABC sequence Y connected source is connected to a delta connected. This is the load which is given here. Calculate the phase and line currents. Okay, and the single phase voltage is given here. Now Z is same. Okay, 8 plus 4. So here no source impedance is not given here. So that means we are going to assume it is 0 source impedance. So the total impedance is just because of the load. Okay. Now the phase voltage is given 100 here, and since it is delta connected, now we need to find out. We need to take root 3 times AN to find out what will be the voltage across the load, and also this 30-degree phase, we saw this also, the line voltage is root 3 times the phase voltage, and also 30-degree phase, additional phase will be there. So that is the reason this 30 has been put here. So once we get the line voltage, then we need to find out the phase currents. Okay, phase currents will be line voltage divided by the impedance. Okay, so you get 19.36 here. The magnitude for the other 3 phase currents also is going to be the same, only the current. So these are all the phase currents. Okay, phase currents, if you see, we are dividing the impedance by the line voltage. So if I go back here, see, the voltage across these impedances are the between two lines, right? You are connected, so it will be the line voltage, right? So that is why we are not dividing the phase voltage by this impedance, but the line voltage. So first we have computed the line voltage root 3 times the phase voltage, and then dividing it by the impedance, and then we are computing the line current. Okay, now line current is again root 3 times and minus 30, okay, of the phase current. If I go back here, now if you say, here we derived it that this current, okay, is algebraic sum of these two currents. Okay, so that is going to be root 3 times this phase current and minus 30. Okay, so that is the reason we compute the line currents here by using this formula. Once we find out the phase currents, so the step is first find out the line voltage divided by the impedance and get the phase voltage, and then from the phase current, and then from the phase current compute the line current. Okay, so this is what it is about. Okay, and then these three, the magnitudes remain same, and they change in they differ only by a phase of 120 degree from each other. So this is known as balanced wye-delta connection. So if we summarize what we have learned today, so there is we learned something known as wye-wye connection, in which the line voltage is given as 3 times phase voltage, and the phase current and the line currents are same. So generally these are the things which are used for transmission, okay, from one because if you see for the transmission, the requirement is to have minimum currents, okay, because to minimize the IR square losses. So when you are along the transmission line, so whenever we are distributing a power supply from one city to other city, or for that matter from the substation to your house also, we generally use a star connected, this kind of connection out here. So these are the loads which are connected at our home, and whenever that electricity department, if we are having a 3-phase supply at our home, then we need to try and ensure that the 3 loads are almost equal. Otherwise the electricity department, if they are giving a single phase power supplies to n number of houses, they do the distribution in such a manner that they are almost the same. So obviously there will be some differences. You can't have practically the exact impedance, but then they will try and match as far as possible. Okay, so here you will find I phase is equal to IL. So these two equations are very important with respect to the wye-wye. Now you can also have these kind of power supply coming to your home, but at your home you can connect a delta load also. Okay, for example, I can have a delta connected motor. So what it does is, see for the same impedance, it is going to drive much higher current. Okay, it is going to take much more current from the system, right? Here the line voltage is √3 Vp, and the phase current is the current which is flowing into your load. So that is going to be √3 times the load current. Okay, so these are used for a high torque mode, since more current means more power, right? So you, for wherever you have high torque requirements, okay, so those kind of where more work requires to be done. So in those applications you can have a delta connected load also. Okay, so we'll stop it here for today. In the next class we are going to learn about delta sources connected to a Y load, and a delta source which is connected to a delta load. So these are the 4 different there are combinations which are possible. So in the next class we will discuss the other 2 combinations. Okay, so that's all for today. Thanks a lot.